Welcome to section 2.5, Solutions by Substitutions. So sometimes we can use a substitution to transform an equation into linear or separable equations. So in this section, we'll look at three types of equations that can be solved using a substitution method. So objective 1 states transform a differential equation using substitution. So suppose we are solving the first order differential equation dy dx. To simplify this equation, we can use a substitution of the form y equals g of xu, where u is a new variable and a function of x. By substituting y, we can express the original differential equation in terms of x and u. So if g has first partial derivatives, we can compute dy dx using the chain rule. Here, the partial g over the partial x is the partial derivative of g with respect to x. The partial of g over the partial of u is the partial derivative of g with respect to u. The derivative of u over the derivative of x is the derivative of u respect to x. Next, we can substitute this expression for dy du into the original equation and also replace y with g. So the original equation was dy dx, which equals f of xy, and now this becomes our partial derivative of g equaling f of x g of xu. Rearranging, we can now solve for du dx, and we get du dx equals capital F, so a whole new function derived from the substitution. If we can determine a solution u of the last equation, then the solution of the original equation is y equals u, or the equation of u. This substitution method can be applied to various types of first-order differential equations. In this section, we will examine three common types of equations that are solvable using substitution: homogeneous equations, Bernoulli equations, and equations with specific substitutions. By mastering these techniques, we can expand the types of differential equations we are able to solve effectively. Objective number 2. Define and solve homogeneous differential equations. This is the first out of 3 that we'll be looking at in this lesson. A homogeneous differential equation is a first-order differential equation that can be written in the form dy dx equals f of y over x, where the function f y over x depends only on the ratio y over x. This means the equation remains unchanged if x and y are scaled by the same factor. You might also see dy over dx equal f of x over y. And in this, our function depends on the ratio x over y. So you might see either one. So for example, dy over dx equals x plus y over x is a homogeneous equation because f equals x plus y over x, which can be simplified to 1 plus y over x, which then depends on y over x. To simplify the equation, we use the substitution y equals v times x. If you're using the other equation, dy over dx equals f x divided by y, then you would use the substitution x equals v times y. But for the purpose of these notes, we're going to stick with the dy over dx equals fy over x. Okay? So we're going to use the substitution y equals v times x, where v equals y over x. So that's just dividing both sides by x. And v is a new variable representing the ratio of y to x. So now we can use the product rule to take the derivative. So dy over dx equals v plus x times dv over dx. We'll replace y with vx and dy over dx in the original equation. So the differential equation now becomes v plus x dv over dx equals fv. Now we can rearrange this to solve for dv over dx. Okay, so we are going to subtract v to the right-hand side, divide by x. Then we'll simplify to get separable variables. So we'll have the v's on one side and the x's on the other. So as we can see, with a small rewrite of the new differential equation, we will have a separable differential equation after the substitution. If the differential equation is a homogeneous equation, we can find the solution by following these steps. Step number 1, verify that the equation is homogeneous by checking if it can be written in terms of y over x. Okay, so if your problem does not state that this is a homogeneous equation that you're working with, you can verify that it's actually homogeneous before following these steps. For step 2, you will use substitution, y equals v times x, and rewrite dy over dx using v and x. If you choose to use your other substitution method, x equals v times y, you are more than welcome to do so. Step 3, simplify and separate variables. Step 4, integrate both sides to find v in terms of x. And then step number 5, back substitute v equals y over x to find y in terms of x. Okay, so let's try some problems. Okay, so in this problem, we're asked to solve the given homogeneous differential equation by using an appropriate substitution. Okay, so following our steps, step number 1 tells us to verify that the equation is homogeneous. Because our problem tells us that the given problem is homogeneous, we're going to trust that it is. All right, so that's step number 1. Step number 2, we're going to use the substitution y equals v times x and rewrite dy dx using v and x. Okay, so for step number 2, we are going to take v equals y over x, which means y equals v over x. We're going to differentiate both sides using the product rule. And we're going to substitute the differentiation into our equation. So we have our equation, so let's write that out. Okay, so in the first part here, we know y is vx, so this would be vx squared, plus y is vx times x dx, plus x squared dy would be v dx plus x dv, which equals 0. And that is the differentiation of y equals vx. We were to take the derivative with respect to x, we would get v dx plus x dv. All right. Next, we are going to simplify this. So we would have v squared x squared plus vx squared dx plus x squared times v dx plus x dv equals 0. We can then distribute the x squares to each term. Let's rewrite that out. You have v squared x squared dx plus vx squared dx plus x squared v dx plus x cubed dv. Okay? And so now we can combine like terms. So we have two terms here that are the same. So v squared x squared dx plus 2v x squared dv plus x cubed dv equals 0. This is actually dx. Okay, so in our first two terms, we can factor out the x squared. So we'll be left with v squared plus 2v dx plus x cubed dv equals 0. Okay, so now we can place our equation in, separate the variables. So we'll have the x variables on one side and the y variables on the other. So let's move the x cubed to the other side. Okay, then I can divide both sides by x cubed and divide both sides by v squared plus 2v. So that will give me x cubed dx and 1 over v squared plus 2v dv. Simplifying this, I get negative 1 over x dx equals 1 over v squared plus 2v dv. And this process is step number 3, where we're asked to simplify and separate the variables. Okay, so in the denominator on the right hand side, let's write this in factored form. So v times v plus 2 dv. Okay, and so now we have it simplified and separable. So step 4 is to integrate both sides to find v in terms of x. Okay, so let's go to the next screen just so we have more space. So for step 4, we're going to integrate. So I'm going to integrate the left side, put the negative outside the integral, and the right side. Okay, when I take the integral of the left-hand side, I'll get the negative natural log of x plus c equals, and then on the right-hand side, I'm going to have to take partial fractions. I'll get 1/2 natural log v minus 1/2 natural log v plus 2. Okay. To get c by itself, I'm going to add the natural log of x to the right hand side. So the natural log of x plus 1/2 natural log v minus 1/2 natural log v plus 2. Okay. And so to get rid of my fractions, I'm going to multiply everything by 2, just so that I have no fractions present. Oops. This actually disappears now. So I have natural log v plus 2. Okay. And so this 2c, since it represents our constant, I'm just going to convert to c subscript 1. All right, because it's still going to be my constant, regardless of whether I'm multiplying it by 2 or not. So C1 will equal, and now this right-hand side I can rearrange using log properties. So the 2 will move to the power, so that'll be x squared plus, so I'm multiplying, and then subtracting v, so I'll divide plus 2. Okay. So I know now that C1 times v plus 2 equals x squared v. So our last step, which is step number 5, is to back substitute v equals y over x to find y in terms of x. So we know that v equals y over x. So I'm going to substitute this into my equation. Okay? So C1 now equals y over x plus 2. Well, it doesn't equal it. C1 times y over x plus 2 equals x squared times y over x. Okay? And so now I'm going to multiply both sides by x so that I can get my x variables out of the denominator. So I will have, and I'll just write it right here, C1 times y plus 2x equals x squared y. Okay. And this would be my solution to my homogeneous differential equation. Okay, our next exercise says solve the given homogeneous differential equation by using an appropriate substitution. Our equation is y dx plus x times the quantity natural log x minus natural log y minus 1 times dy equals 0. And our initial condition is y of 1 equals e. So our first step tells us to verify whether it's a homogeneous equation or not. Since our problem already tells us that it's homogeneous, we do not need to verify. All right. All right, step number 2. We are going to use substitution and rewrite dy dx using v and x. So let's use our other substitution equation where x equals v times y. So then v equals x over y. Okay. So in starting with our equation, we have y dx plus x times the natural log dy equals 0. Okay, we are then going to substitute in the differentiation of v. So we have y, and then dx will equal the derivative of x will equal v dy plus y dv plus x equals vy times the natural log of vy minus the natural log of v minus 1 dy and 0. Okay? Next, we can distribute the y in the first term. So we have vy dy plus y squared dv plus vy. And then the natural log of v times y, we can use the log properties and separate those by addition. So the natural log v, natural log y. Okay, and we see here the natural log y minus the natural log y cancel each other out. Okay, so we're left with vy dy plus y squared dv plus vy times the natural log of v minus 1 dy equals 0. We have two terms that are alike, so we can combine them. So we'll have vy plus vy natural log v minus 1 dy plus y squared dv equals 0. We can now factor out a y from our first term. So y times v plus v, natural log v minus 1. Let's make those brackets just so that you can see it a little clearer. Let's make those brackets. Okay, dy plus y squared dv equals 0. Okay, and so now what we can do is factor out a a v from our grouping in this parentheses. So we technically could have factored out a v and a y in this step. So let's do that actually. So when we factor out a v, we'll have, let's rewrite that. So when we factor out a v and y, we'll have 1 plus the natural log v minus 1. So the 1 and the minus 1 cancel out. So we are left with vy times the natural log of v dy plus y squared dv equals 0. Okay, and so that's step 2. So for step 3, we can now simplify and separate variables. Okay, so we need the y variables on one side and the v variables on the other side. So I'm going to subtract the y squared to the other side. Then I'm going to divide both sides by negative y squared and divide both sides by v times the natural log of v. So I'll have y squared dy and then 1 over v natural log v dv. And then I can simplify. So this is negative y, negative 1 over y dy equals 1 over v natural log v dv. Okay, so this is now the completion of step number 3, where I was able to simplify and separate variables. Okay. All right, let's go to the next slide and start number 4. Okay, so I'm just going to rewrite my previous step just so that we know where we're starting with. Okay, so then step number 4 is to integrate both sides to find v in terms of x. So now we are going to take the integral of both sides, integral. Okay, and let's let v, let's do a different one since we already working with b. So let's let u equal the natural log of v. So that means du will equal 1 over v dv. Okay, so then we have the integral of 1 over y dy equals the integral of 1 over v dv. Okay, actually that v should be u. I should have used a different variable because u and v's can get mixed up, but let's continue. It's okay. All right, so I know du is 1 over v, and then I have the natural log of v, which is u, so that would turn into 1 over u du. So when I apply the integral, I have the negative natural log of y plus c equals the natural log of u. I know u is the natural log of v, so I can rewrite that as the natural log of v. So the natural log of the natural log of v. So then c equals the natural log of y plus the natural log of the natural log of v. Okay. So then for step number 5, we're going to back substitute. Okay. So in back substitution, we know v equals x over y. So c then is going to equal the natural log of y plus the natural log of the natural log of x over y. We can exponentiate both sides. So we'll have e to the power c, and then we'll have y times the natural log of x over y. So we can combine or simplify e to the power c and just make that one constant. We'll give it c1. And so c1 equals y times the natural log of x over y. Okay. All right. So that is our general solution. But now we need to do our final step, number 6, because we're working with an initial value problem. We're going to let y of 1 equal e. So c equals e times the natural log of 1 over e. So that means e times the natural log of 1 minus the natural log of e. So e times, and this quantity simplifies to -1. So c equals negative e. So our solution with this initial condition is e, or negative e, equals y times the natural log of x over y. Okay, so the first one is our general solution, and then the second is our particular solution. All right, awesome. All right, objective number 3, define and solve Bernoulli differential equations. A Bernoulli equation is a first order differential equation of the form dy over dx plus p of x times y equals f of x times y to the power n, where p of x and f of x are functions of x and n is a real number. Key cases when dealing with Bernoulli equations is if n equals 0, then the equation reduces to a linear equation. If n equals 1, then the equation becomes linear and separable. But for when n does not equal 0 and n does not equal 1 cases, to transform the equation into a linear equation, we need to use substitution. And the substitution equation we're going to use is v equals y to the power 1 minus n. So why use this substitution? Well, the substitution simplifies the nonlinear term y to the power n. And since v equals y to the power 1 minus n, we have y equals v to the power 1 over 1 minus n. If we differentiate v with respect to x, we have dv over dx equals 1 minus n times y to the power negative n times dy dx. Rearranging this for dy dx, we get 1 over 1 minus n times y to the power n dv over dx. And this then is a linear differential equation that we can solve for v, and once we have this in hand, we can also get the solution to the original differential equation by plugging v back into our substitution and then solving for y. So it's very similar to the last problem. It's just another form of substitution when our differential equation is written as a Bernoulli equation. So if the differential equation is a Bernoulli equation, we can find the solution by following these steps. So first we're going to identify if it is written in the Bernoulli equation format and determine our n. Then we will use substitution where v equals y to the power 1 minus n, rewrite the equation and then simplify. And then we'll solve the resulting linear equation for v. Then we'll back substitute v to find y. Okay. All right, let's do a problem together. So here we are asked to solve the given Bernoulli differential equation by using an appropriate substitution. So our equation is x times dy over dx minus 1 plus x times y equals x y squared. Okay, so we want to, in step number 1, we want to identify this equation as a Bernoulli equation and determine n. So our equation, x times dy dx minus 1 plus x times y equals xy squared. We are going to divide x in order to isolate the dy dx by itself. So we'll divide everything by x. So we'll get dy dx minus 1 plus x over x, y equals y squared. Okay, so from this, we can identify our p of x as negative 1 plus x over x. We can identify the f of x as 1, and our n is 2. Since n does not equal 1, this is a Bernoulli dE, and we can apply the substitution. Okay, and the substitution that we're going to apply now goes into step number 2. Oop. Let's rewrite that. Step number 2. Okay, so v equals y to the power 1 minus n. Our n here is 2, so 1 minus 2 is negative 1. So v equals 1 over y. Okay. If we differentiate both sides, dv over dx equals negative 1 over y squared times dy dx. Okay. We can rewrite this in terms of dy dx to isolate that by itself, and we get negative y squared times dv over dx. Okay, so now that we know the expression for dy dx, we can substitute this into our original equation. Okay, so when we do that, we'll have negative y squared dv dx minus 1 plus x over xy, or over x times y equals y squared. Okay, and this right here is my original equation that I substituted dy dx expression for. Okay, now I can divide everything by negative y squared, so I'll get dv dx isolated. So I have 1 plus x over x, and this will then be times 1 over y when you simplify, equals negative 1. Okay, and so that's step number 2. Step number 2 was to use substitution and rewrite the equation and simplify. Okay, so now we're going to solve the resulting linear equation for y. Okay, so we're going to replace our 1 over y for v. Okay, and we're then going to solve this using one of the steps that we've previously learned. So let's go to the next page here. So this is step 3. Okay, so we had dv dx plus 1 plus x over x times 1 over y equals negative 1. So I'm now going to replace 1 over y with v. And now I'm going to use this to solve for v. Okay, So I'm going to find my integrating factor. So p of x equals 1 plus x over x. Q of x equals -1. So mu of x equals e to the power integral of p of x dx. So that means e to the power 1 plus x over x dx. I'm going to simplify my power. So I'm going to split my integral into 2. So I'll have dx over x plus the integral of dx. So 1 times dx, so just dx. When I simplify this, I will then get the natural log of x plus x. So my integrating factor is e to the power natural log x plus x, which I can separate and then simplify. So my integrating factor is x times e to the x. Okay. So now that I have my integrating factor, I'm going to multiply every term in my equation by my integrating factor. So x times e to the x times dv dx plus x times e to the x times 1 plus x over x times v equals x times e to the x times -1. Okay. I know that this is the answer to the product rule of the derivative of x e to the x times v with respect to x, and that equals -x e to the x. So I'm going to then take the integral of both sides. Okay. And this is dx. Okay. And then I'm going to, oh, forgot my dx here too. Let's see if I can fit that in there. dx. There we go. All right, then I'm going to simplify. So I'll have x e to the x v equals -x e to the x, and then take the integral of e to the x, which is e to the x, and then plus c. So to solve for v, I'm going to have to divide everything by x e to the x. So I'll have -x e to the x plus e to the x plus c, all divided by x e to the x. Simplifying this, I'll have -1 plus 1 over x plus c over x e to the x. So now I can back substitute. So I know that v equals 1 over y. So v equals 1 over y, which is the same thing as y to the -1. So I have y to the -1 equals -1 plus 1 over x plus c over x e to the -x. I just moved e to the x to the numerator. Okay, and that's my solution. Whew, that was a lot of fun. All right, our next problem is also a Bernoulli equation. All right, but in this equation, we now have an initial condition. Okay, but we're going to take the same 4 steps that we took on the previous problem. It's just we have one more step because we have an initial condition y1 equals 1/2. Okay, so first let's identify our equation as a Bernoulli equation so that we can then identify our substitution. So for step number 1, we have x squared dy dx minus 2xy equals 3y to the 4th. So we're going to divide everything by x squared in order to isolate the dy dx. So that will give us dy dx minus 2y over x equals 3y to the 4th over x squared. Okay, so according to the Bernoulli equation, p of x would be negative 2 over x, f of x would be 3 over x squared, and n would be 4. So since n is not 0 or 1, we know that this is a Bernoulli equation and we can apply substitution. So for step number 2, our substitution will be v equals y to the power 1 minus n. Since n is 4, v is going to equal y to the negative 1/3, or 1 over y to the 3rd. Okay. When we differentiate both sides of our substitution, we'll have dv over dx, which equals negative 3 times 1 over y to the 4th times dy dx. Okay. We can rewrite this to isolate dy dx by itself, and we'll get negative y to the 4th over 3 dv dx. Now that we isolated dy dx, we can substitute this into our original equation. So we'll have negative y to the 4th over 3 times dv dx minus 2 over x y equals 3 over x squared y to the 4th. We can divide everything by, let's divide everything by negative y to the 4th and then multiply everything by 3. Okay, that way we get dv dx by itself, making a linear equation, which we can then solve to get v. So we'll multiply everything by 3. So let's do that, multiply everything by 3. And then we're going to divide everything by negative y to the 4th power. So if we simplify this, if I divide by negative, so that will make it positive, and then y over y to the 4th will give me 1 over y cubed. And then 9 over x squared, and if I divide by y to the 4th, that will cancel for 1, but it is negative. Okay. Now I know that 1 over y to the 3rd is v. Okay, so I can rewrite this. So 6 over x v equals negative 9 over x squared. Okay, and so now I can solve this for v. So this is step number 3. All right, we're going to solve the equation for v. So I'm going to find my integrating factor. So my p of x is 6 over x. My q of x is negative 9 over x squared. So mu of x is e to the power integral of p of x dx. So that's e to the integral of 6 over x dx. Simplify, I get e to the power 6 natural log of x. So my integrating factor is x to the 6th power. Okay, so now I'm going to take my integrating factor and multiply it by each term in my linear equation. So I'll have x to the 6th power times dv dx minus x to the 6th power times 6 over xv equals negative x to the 6th power 9 over x squared. Okay, oh, and this is plus. All right, so I know the left side is going to be the derivative of x to the 6th power v dx equals, if we simplify the right-hand side, negative 9x to the 4th. If we integrate both sides, okay, we'll get x to the 6th v equals negative 9 over 5 x to the 5th plus c. Getting v by itself, we'll have to divide everything by x to the 6th power. So we have negative 9 over 5. And that will get us x to the negative 1 plus c over x to the 6th power. Okay. Now for step number 4, we back substitute. All right, we know that v equals y to the negative 3rd. So y to the negative 3 minus 9 over 5 x to the negative 1 plus c x to the negative 6. That is our equation for y. But we're not done. We know this is an initial value problem, so we have an initial condition. So we're going to let y of 1 equal 1/2. So substituting that into our equation for y, we have 1/2 to the power negative 3 equals negative 9 over 5 times 1 to the negative 1 plus c times 1 to the negative 6. So 1/2 to the negative 3rd or 3 is 8. Then we have negative 5 over 9 plus c. And so then c will equal 49 over 5. So our solution with this initial condition is y to the negative 3 minus 9 over 5 x to the negative 1 plus 49 over 5 x to the negative 6. This is our particular solution. Okay, great. Okay, objective number 4. So this is the third type of problem involving substitution. So we're going to solve a specific type of differential equation. So the differential equation of the form dy over dx equals f of ax plus by plus c involves the function f of the linear expression ax plus by plus c, where a, b, and c are constants. This type of equation can always be reduced to a separable equation. So to simplify the equation, we're going to use substitution. So we're going to let u equal ax plus by plus c, where b does not equal 0. This substitution represents the argument of the function f. Then we can differentiate u with respect to x. So we'll get du over dx equals a plus b times dy dx. We'll rearrange to express dy dx in terms of du dx. Then we'll substitute u and dy dx into the given equation. Okay? Then multiply through by b to simplify, and then rearrange in order to isolate du dx by itself. Okay? So with this substitution, we'll be able to rewrite the original differential equation as a new separable differential equation so that we can then solve it using the methods we already know. So in summary, to find the solution, we're going to identify the equation dy dx equals f of ax plus by plus c. Then we're going to substitute u for ax plus by plus c and rewrite dy dx in terms of u. Then we'll simplify and separate variables to get du and then g of u equals d of x. Then we'll integrate both sides. Then we'll back substitute. So we'll input our expression for u to return it back to the original variables. Okay, so let's apply these to our next problems. All right. For our first problem, we are asked to solve the given differential equations by using an appropriate substitution. So for step number 1, we're asked to identify the equation dy dx that is given to us. All right, our equation has dy dx isolated already, so no further multiplying, dividing needs to happen. Next, we're asked to substitute u for our ax plus by plus c and rewrite dy dx in terms of u. So let's first let u equal y minus x plus 5. Okay, so if we do that, our dy dx will equal 1 plus e to the power u. Okay, now we want to differentiate both sides of our u expression, right? So du dx will be equal to dy dx minus 1. Okay, so we differentiated both sides of our u equation. So now we can substitute dy dx. So du dx equals 1 plus e to the u, power u, minus 1. So du dx equals e to the power u. Okay, so that's step 2. Step number 3 says to simplify and separate variables to get du over g of u, so that's our equation in terms of u, equal to dx. Okay, so we have du over dx equals e to the power u. So to rearrange this equation, we'll just have du over e to the u equals dx. Okay, and we can rewrite this as e to the negative u du equals dx. Okay, so then step number 4, We are now going to integrate both sides. Okay. And we'll get negative e to the negative u equals x plus c. Okay. And this then is our general solution. So for our last step, number 5, we need to now back substitute. Okay, so we're going to substitute our expression for u to return our equation back to its original variable. So we'll have negative e, and this is supposed to be negative u, okay, to the negative y minus x plus 5, and the exponent equals x plus c. Okay, and then we can simplify the power. We'll have negative y plus x minus 5 equals x plus c. All right, awesome. Okay, so our next problem in this objective is to solve the given dE by using appropriate substitution. dy over dx equals cosine x plus y, where we have an initial condition y of 0 equals pi over 4. Okay, so following the same steps as in the last problem, we just have one extra step at the end is to apply that initial condition. So our problem is already identified as dy dx. It's already been isolated. So we can now move on to step number 2 with our u equaling x plus y. Okay, so that means dy dx equals the cosine of u. If I differentiate both sides of my u equation, I'll have du dx equals 1 plus dy dx. So I differentiated both sides with respect to x. So now I can substitute in my dy dx into this differentiation. So du dx equals 1 plus the cosine of u. Let's put u in parentheses. There we go. All right, now I can separate my variables. Okay, so this is now in step number 3. All right, so when I get all the u variables on one side and x on the other, I will have du divided by 1 plus cosine u equals dx. Okay. All right, so that's step number 3. So to get to step number 4, where I want to integrate both sides, we're going to simplify, or I guess you could say rewrite this expression so that we can then take the integral. So we're going to multiply the ratio by the conjugate of the denominator. So we're speaking to the left side of this equation. So we're going to multiply the numerator and denominator by the conjugate. So we'll multiply the top and the bottom by 1 minus cosine u. In doing so, our denominator now becomes 1 minus cosine squared u. Okay. So then we can use the trig identity, where cosine squared x plus sine squared x equals 1, to rewrite the denominator. Okay, so we're doing this so that we don't have a trig function in our denominator. sine squared u. Okay. And so if we were to simplify this, we would have 1 over sine squared u minus cosine u over sine squared u, which equals cosecant squared u minus, and this ratio can be split up again to 1 over sine u times cosine u over sine u. So this would then equal cosecant u cotangent u. Okay, so that's the left-hand side. All right, so for step number 4, we'll take the integral of cosecant squared u minus cosecant u cotangent u du equals the integral of dx. All right, and so this will then equal negative cotangent u plus cosecant u, which equals x plus c. All right. So for step number 5, we can now back substitute. So in back substituting, we had cotangent u plus cosecant u equals x plus c. So we know what u is. That is x plus y. So we can enter that in. X plus y equals x plus c. So that is our general solution. So that's step number 5. So step number 6 now is to apply our initial condition. So we're going to let y of 0 equal pi over 4. So negative cotangent of 0 plus pi over 4 plus cosecant 0 plus pi over 4 equals 0 plus c. So this would be cotangent of pi over 4 is 1, but we have a negative in front, so that's a negative 1. Cosecant of pi over 4 is the square root of 2, and 0 plus c equals c. So c equals the square root of 2 minus 1. So our particular solution then is, I'm going to rearrange this so that I have a positive. Starting first, cosecant x plus y minus cotangent x plus y equals x plus the square root of 2 minus 1. And that is our particular solution for this problem. All right, that concludes section 2.5. Enjoy.